Okay, so now we have an idea of what the energy eigenvalues are, and we see that in fact, again, they agree with what Bohr had predicted. Bohr's model was phenomenological. Now we have, although again we haven't gone through the gory details of the derivation, now we have a quantum mechanical motivation, a quantum mechanical underpinning for this formula here. And for each energy eigenvalue, we have an eigenfunction, a radial solution. Okay, these an R, and R depends on N and L. Okay, and this is the nasty form that that the radial solution takes. Okay, and we see that there's this constant A naught that pops up. A naught is called the Bohr radius, and it's a combination of constants: 4 pi epsilon naught h bar squared over m e squared. M is the mass. In this context, m is the mass of the electron. We should probably maybe put a little subscript e. That's the mass of an electron. And again, E is the elementary charge. Okay, N is the principal quantum number, and L is the quantum number which is related to the total angular momentum, as we discussed before. Okay, so we have these factorials. We have an exponential function. This should be A naught. We have these. Now we have these functions, these Laguerre functions. Okay, so the L's. Okay, the L's, which has a subscript and a superscript, LQ. So LQP is is called an associated Laguerre polynomial. Excuse me. And some of the associated Laguerre polynomials are shown here. L00 is equal to 1, L02 is equal to 2, 01 is equal to 1, 10 is equal to minus x plus 1, etc. Okay, you have, as you go up, as the subscript increases, we see that we have a polynomial of one higher order. Okay, so polynomial of order 0 means that you have a constant. Polynomial of order 1 means that you have order of power of x to the first power, and then the L sub 2's have of x to the second power. Okay, and very importantly, when now we have a restriction on the allowed values of L, again the quantum number that characterizes the total angular momentum, L now can't take on just any integer values. Before we saw that L could be, when we looked at just the radial equation, we had no restrictions on L other than it had to be greater than or equal to 0, an integer greater than or equal to 0. And now we see that when we incorporate the radial solutions, that L can now only run from 0 to n minus 1. So whatever the principal quantum number is, L can only go up to that minus 1. Okay. So now here are the Laguerre polynomials. Now these are expressed as a function of x, but in our case, the argument for the Laguerre polynomials is 2r over n times 2r over n a naught. Okay, and you see also that the QP's are n minus l minus 1 and 2l plus 1. Okay, so those are the radial solutions to the hydrogen atom potential. Okay. Now recall that the total wave function solutions in the central force potential are a product of these radial solutions, which we just found, and the angular solutions, which we found in previous lectures.